Okay, we're going to take a look at this problem from Lecture 6 on applying the Work-Kinetic Energy Theorem. So this sapling question says, a boy shoves his stuffed toy zebra, which has a mass m, down a frictionless chute starting at height d. So he takes a little zebra, he stuffs it down the chute. We're beginning a distance d above the ground, and this has an initial speed v. And then it says the toy emerges horizontally from the bottom of the chute and continues sliding along a horizontal surface with coefficient of kinetic friction, mu. So the zebra comes out the bottom and it slides this way and comes to rest, so v is 0 there, a distance lowercase d from the bottom of the chute, and this surface has friction, but the chute is frictionless. Okay, so we're trying to find d. So the work-kinetic energy theorem tells us that the net work done on an object is the change in that object's kinetic energy. Okay, so how do we find the net work? Well, the net work is the sum of the works done by each force that acts on the object. So what forces exist in this situation? Well, gravity is at work here. The zebra's going down the chute, so there's a normal force. So as the zebra slides along the inside of the chute, there's a normal force that points in a direction perpendicular to the direction of motion. And we still have gravity. And when the zebra comes out over here, again, at each point there's a normal force, there's a gravitational force, and there's a friction force that points back this way. Okay. So we need to add up the work done by gravity plus the work done by the normal force plus the work done by friction equals delta KE. So what's the work done by gravity? Well, we know that the work done by some force is that force dotted with the displacement of the object. So the work done by gravity, so gravity is always acting straight down. So if we consider the path of the zebra, whenever the zebra moves laterally, gravity does no work. But if the zebra moves up and down, gravity is doing work. So we just need the total amount that the zebra's gone up and down, and that total amount is d. So the work done by gravity is the force of gravity acting on the zebra times d. And the cosine of those two, when we do the dot product, we're doing F delta R cosine of the angle between them. And in this case, gravity points down and delta R points down because the zebra is moving down. Then we're going to add the work done by the normal force. Now, at each point, the normal force is perpendicular to the direction of motion, which means that delta R is in the direction of motion. So delta R is always perpendicular to the normal force. So this work will be 0. And then we just need to add the work done by friction. So that's going to be the friction force dotted with the displacement, which is little d. And that equals the change in kinetic energy. Change in kinetic energy is the final kinetic energy minus the initial kinetic energy. Okay, so the force of gravity is in the same direction as D, so that's a positive work. So we just have mgd. The force of friction is this way, but the displacement is to the right. So this has to be negative work. So we actually have to subtract mu times the normal force, which in this case is mg, times d. The final kinetic energy is 0 because it's not moving at the end. And the initial kinetic energy is 1/2 mv initial squared. So at this point, we see that the mass of the zebra cancels. And we're solving for small d, so I'm going to move gd over to the other side. So we have minus mu g little d equals minus 1/2 v squared minus g times d. Let's do the negative sign, everything becomes a plus. So little d is equal to 1/2 v squared plus gd minus, divided by mu times g. And that's it. You could rewrite this if you wanted to, but you don't have to. That should work just fine.